And we will switch over to Mariadebora Mauriello from Marseille, working together with Southampton.
So thank you for the introduction. I am Mariadebora Mauriello from the University of Marseille. And today I'm going to present some results that I obtained with a collaboration with the University of Southampton and also with my supervisor, Lionel Archevêque and Pierre Dupont. The title of this study is No Linearities Induced by a Deterministic Forcing in Transitional Shockwave Underlayer Interaction. First, I will introduce the typical behavior in the case of transitional shockwave underlayer interaction. Then, as I said, we switch and we try to use a deterministic forcing. So I will define the 4 test cases that we set for this study. First of all, we want to understand if also with the deterministic forcing, we were able to have unsteady interaction. But to answer to this question, we had to go through, I call it no linear game. And we found that there is a no trivial triple between frequency, wave number, and locations. And based on this result, we were able also to depict the frequency space organization of the flow. And finally, some conclusion. So first, when we speak about the transitional SBLI, we are speaking on an incoming laminar boundary layer that it interacts with a shock system. So the first shock that we encounter is the impinging shock, and the pressure rise that the impinging shock, due to the impinging shock, is traveling upstream. So the boundary layer separates, and at the so-called separation point, what we have is a pocket of compression waves that they are moving at low frequencies. Because of the separation of the boundary layer, we have 2 different velocity that leads to a mixed layer along the separated streamlines. After the impinging shock, what we observe is an expansion fan. That means that the flow field, that means that the flow is accelerating again, and because of that, it reattaches thanks to a so-called reattachment shock. This region is also characterized by the transition of the boundary layer from laminar to turbulent. And what we know from the literature is that this transition, in the case of low supersonic Mach number, is mainly driven by the breakdown of the oblique mode. The oblique mode are 3D instability boundary layer modes, and along the mixed layer, their amplitude linearly grow until a point where they enter in the nonlinear stage and the transition of the boundary layer occurs. What we were interested in was to understand if there is a link between the nonlinearities of the oblique mode, this link between the nonlinearities of the oblique mode and low frequency that are occurring at the separation point. So we numerically study a transitional SBLI configuration based on the which inflow parameter were based on the experimental measurement that were made by Moussa Diop at the University of Marseille and are documented in his work. And we answered to this question, and we found that indeed exists a quadratic coupling between the oblique mode and the separation point. Numerically, we found at the separation point that the Stern number is 0.055. How we answer to this question? By using nonlinear tools. In the frequency domain, we computed the bicoherence map. I'm not going into detail of the bicoherence maps, but what we have to know is that thanks to the bicoherence tool, we are able to highlight the nonlinearities, the nonlinear coupling that is occurring in a selected zone of the flow that we want to investigate. In that case, we selected the apex of the separated region where the breakdown of the oblique mode is occurring and the separation point. And what we found is that this nonlinear coupling indeed is in a frequency band that is that is characteristic of the low frequency unsteadiness. So the first conclusion was that the high frequency modes are quadratically coupled with the large scale low frequency features that are located at the separation point. We also use another tool from the nonlinear analysis that is in the frequency wave number domain. That is again the Backwaren maps, but in the wave number domain. And what we found is that the trace of the quadratic coupling in the wave number domain is 2D. So the flow features that are able to sustain this low frequency oscillation are at the separation point are 2D. Two important conclusions from the previous study. So first, that the oblique mode are quadratically linked with these flow features at the separation point. And second, we found that the nature of this flow feature is 2D. One key point of this simulation was that at the inlet, we said broadband and stochastic inflow perturbation. That means that was directly the mean flow to naturally select which were the most unstable mode that were leading to the transition. So the question that we were asking was what happens in the case we instead use controlled deterministic forcing. So from here, the collaboration with the University of Southampton, and we decided to run numerical simulation on a transitional impinging reflecting shock configuration that based on the aerodynamic parameter of the work of Stansica. And the difference between this new study and the previous one is the way we forced the inflow. So in this new case is a modal forcing technique. That means that we have the inflow perturbation that are superimposed to the mean flow that are completely deterministic and controlled. That means that their shape comes from the linear stability analysis. And there are some fundamental parameters that we can control, and they are the streamwise wave number, that is the wave number aligned with the flow direction, the span-wise wave number, beta, that can be positive and negative, and also the pulsation, omega, at which this fluctuation can pulsate. And A0 is the amplitude of the inflow perturbation. It usually is very, very low. And Q hat instead is the shape that comes from the linear stability analysis. Since we wanted to have transition, we need to have allow quadratic interaction. So we need at least two waves of family. The way we selected these two waves family is such that they are equal in the space organization. So that means the streamwise and the span-wise wave number are equal for the two family, but they differ in the pulsation. So that means that delta omega between the two family is such that it corresponds itself in the value of the Strual number that is characteristic of the low frequency unsteadiness. So we have the delta omega corresponds to the Strual 0.04. Another characteristic of these simulations is that there is periodicity in the sense that we checked that the separated region was deterministic and periodic with a period that corresponds to the minimum frequency that again corresponds to the delta omega that fell in the low frequency in the Strual 0.04. And that allowed us to process one period simulation. Before introduce the four test cases that we analyzed, some notation. So with the subscript plus, I'm going to indicate the family with the positive wave number in the span-wise direction, and the minus is the opposite, so the negative one. And with the subscript 1 is the family that is governed by, that is moving frequency corresponding to the pulsation omega-1 and 2 instead the pulsation omega-2. These are the 4 test cases that we decided to study. The first one is the beating oblique waves, in which we selected all the possible combination of the perturbation that we have defined. So for the first family, we have positive and negative span-wise wave number, and the same for the second family. In the case of the parallel oblique waves, instead, we selected only the combination that give us the positive wave number. For the crossing oblique waves, instead, we selected from the first family positive wave number, span-wise wave number. For the second family, instead, the negative span-wise wave number. And the last combination is crossing oblique waves plus the streak. What is characteristic of the streak is that they are stable over time. That means that the frequency is equal to 0. And the span-wise organization that we have is at least twice is an integer of the wave number of the oblique mode. And in that case, we decided to set it equal to beta. That means twice the span-wise wave number. First, we observed for this 4 combination, the length of the separated region and the downstream flow. We decided to set the length. I mean, the length of the separated region is defined as the distance between the reattachment and the separation point. And in this plot, I'm showing the profile of the friction coefficient for all the different family. What we can observe is that for the beating waves, for the crossing waves and the streak waves, the length of this region is almost the same. But in case of the parallel waves, it is longer. It starts to separate before and it reattaches downstream with respect to the other cases. What is also interesting is that there is no difference in the separated region, in the length of the separated region for the crossing and streaky waves. So we can conclude that the streak did not influence the length of the separated region. If we focus our attention on the downstream flow, what we have is that for the beating, the crossing, and the streaky waves, the flow start to become turbulent. It is approaching the turbulent profile. Instead, the CF, in the case of the parallel waves, after the reattachment point, it approached the laminar trend. What we concluded is that the parallel combination is less prone to promote the transition. After that, we want to understand if in these 4 combinations, we were still able to have unsteady interaction. So the first tool that we used was the power spectral density of the wall pressure fluctuation at the wall, or the wall pressure fluctuation field for all the 4 cases. And in this spectrum, I normalized the streamwise dimension with the length of the separated region and the frequency with, again, the length of the separated region and the external flow, such that to obtain the Strual number. And again, in each spectra, I also indicated with the 2 vertical dashed line the point at which the flow separated area touched, so 0 and 1. Instead, with the horizontal white line, I'm indicating the forcing frequency. There are actually 2 forcing frequencies, but the difference is marginal. So in the plot, it looks that there is just 1, but there are 2 actually. And the first observation that we can make is that starting from the forcing frequency, we have a cascade of the energy to all the harmonics starting from the first one. So indeed, we observe the energy cascade. And this is true for the beating oblique waves, for the crossing and the streaky family, but not for the parallel family. And we already observed that by looking to the friction coefficient profile. If instead we focus our attention on the separation point, we still have the strand number that is associated to the low frequency range. But in the case of the emitting oblique waves and the parallel oblique waves, the content at the separation is five order of magnitude higher than the case of the crossing and the streaky family. In particular, it is barely visible for the crossing family. Obviously, the difference between the crossing and the streaky families is the streak, but is only the streak, the difference. So we start to play a nonlinear game. This nonlinear game with the Fourier modes. Before continue and speak about the nonlinear game, we have to remember which was the result that we obtained with the previous study. We obtained that we have a trace of the nonlinearities at the separation point that are giving throughout that is in the low frequency range for structures, for flow features that are 2D. Say that we start with the crossing oblique waves, and we have seen that they are described by pulsation and wave number. The first is given by wave number that is positive, Q1 plus, and the second one is given by the pulsation 2 and wave number negative, minus beta. Since the data are real, we are performing the Fourier transform, and because of the Hermitian symmetry, we also have to consider the complex conjugated. And if we combine, the possible combination that we obtain are 4. Among these combination, we are interested in one that have the delta omega that is positive, and in particular that lie on the low frequency range. And among these two, the one that respect these two constraints actually result in a 3D flow features. So possibly the crossing oblique waves do not give any low frequency content because the 2D flow feature, because the flow features at the separation point are 3D. But so far we don't know where are located these 3D features. If we do the same for the streaky family, we obtain the same result. So we still have 3D flow features in the low frequency range. But if we also add the contribution of the streak, what we have is that we may have cubic interaction of the Blake mode and the streaks. And what we obtain is indeed this cubic interaction leads to 2D flow features in the low frequency range. To be complete, I also did math for the other cases. And what we obtain is that for considering the low frequency range, for the beating waves, we obtain both 2D and 3D flow features. The crossing wave and the streaky waves are only 3D. The parallel waves instead pure 2D. In the case of the streak, if we also consider the streaky family, if we also consider the streaks, we have cubic interaction that give us 2D flow features. But again, where are they located? These 2D flow features that are able to support low frequencies. To understand this not trivial trouble between the frequency, wave number, and location, we performed wave number, frequency, power spectra. We computed the wave number, frequency, power spectral density of the wall pressure fluctuation field, and we fixed the frequency to the low frequency range. And in this spectra, what I'm plotting for each case is the streamwise evolution normalized with the length of interaction and the corresponding and the organization in terms of the wave number that in that case is normalized such that to obtain the inverse of the domain wave. And what we are looking for the beating oblique family, what we have seen from the previous table is that we have 2D and 3D structures. And from this spectra, we are able to say that the 2D flow features are indeed localized starting from the separation point. For the parallel oblique waves, these spectra again give us the information that the 2D flow features are localized starting from the separation point towards all the domain. In the case instead of the crossing and streaky family, the 3D flow features are no more are localized only from the reattachment point towards downstream. So there is no trace of 2D flow features at the separation point. But as I mentioned it before, from the simple power spectra, the energy content in the case of the crossing and streaky family was 5 orders of magnitude lower than the beating and parallel families. So if we reduce and we saturate the plot such that to reduce the contour, for the streaky family, indeed, we observe some content already at the separation point. And most probably, again, these 2D flow features are coming from oblique, cubic interaction. So two important conclusions from this spectra is they are that when parallel combination is included, that means that for the low frequency range, 2 k zeta equals 0 is observed at the separation point. And the other conclusion is that the streak might be active in cubic couplings. We wanted to understand also the quadratic coupling that is occurring among these 4 family. And so for that, we exploit the bispectral analysis. That is a tool that allows us to detect and quantify the nonlinearities, but we had a problem because of the periodicity and the one period simulation that we computed with in that case. So we couldn't average in time over the block. But at the same time, we had a trace, we had a signature of the nonlinearities in the both frequency and wave number space from the previous study. So knowing this trace in the wave number space, we computed the wave number bispectrum. That is, it allows to highlight the nonlinearities in the wave number space, considering the nonlinear interaction between the 2 first space Fourier transform, G1, G2, that are resulting in the third space Fourier transform, G3. And this wave number bispectrum, so is the function of the 2 wave number, but also the time delay that is between the first 2 series. Because we introduced the time delay, we were able to perform the simple Fourier transform of this bispectral quantity. So what we obtained is the frequency transformed space bispectrum. That is the simple power spectral energy content that is associated with the bispectral quantity. In that case, is the wave number bispectrum. So we are able to highlight the quadratically coupled space Fourier modes, frequency by frequency. And these are the corresponding spectra. What we are plotting here is the norm of the Fourier transform of the wave number bispectrum. And it allowed us to directly highlight the quadratic coupling that is occurring between two different locations of our flow configuration for a selected wave number that we know that has to be 2D to have low frequency at the separation point. And we were able to understand which was the location where we have these nonlinearities and the corresponding range of the Strual number. And what we observe is indeed for the beating and the parallel family, we have 2D flow features starting from the separation and even upstream the separation point for a Strual number that fall in the low frequency medium range. And for the case of the streaky family, we obtain the same, but the content is lower if compared to the beating and parallel family, but no trace of quadratic couplings in the simple pure crossing combination. So the first conclusion that we had is, again, when parallel combination is included, and it is included in both the pure parallel family and the beating family, we have that the 2D flow features are at the separation point, and they are responsible. They can support the low frequencies that characterize the head shock. And in the case we have just crossing oblique waves, if we also introduce the streak, then we have the same scenario. To summarize everything, for the parallel combination, what we obtain is that we observe a longer separated region, and we observe also that it is less prone to promote the transition at the reattachment point. Instead, for the crossing combination, we obtain the shorter separated region, and the transition boundary layer is observed at the reattachment point. Moreover, for the parallel combination at the separation point where we observe low frequency unsteadiness, we found that the nature of the flow features is 2D. In the case of the crossing combination, instead we observe just a marginal level of low frequency unsteadiness, and the flow features are 3D. But the scenarios change if we also include the streak. So, thank you.